Hello, this is Michael. This is a 360-degree video. So if you're watching on YouTube, you can drag the video with your mouse and pick whatever angle you want to look at. If you're watching in VR, just look around. It's pretty cool. Anyway, so this is my remote observatory. The wiring is horrible, so it works, but you get it neat at the beginning and then kind of adds on after time and becomes not neat. So anyway, ignore the mess. But this is what my remote observatory looks like. We'll just do a quick pass around of the electronics here. Network switch gear, cellular router, let's see, power switch, HDMI switcher with a remote capable IPKBM, power inverter that is only used when I'm here and need to plug something in. This is my solar controller, so that brings in the solar power. Breaker to disconnect solar panel. These are Tesla lithium-ion batteries, and they're 24 volt nominal. So this converts that 24 volt down to 13.6 volts, which is what runs all the astronomy equipment. The flap that is down right now, you might be able to see depending on sun glare, and the roof that's open all the way at the other end there that you can see. Those are both 24 volt controlled, so they get lower current, higher voltage to do the same work. Security camera down there, if you can see that. Motion sensor, temperature sensor, a bunch of other stuff. Some floodlights in case I'm working in here and need some light. The Tesla lithium-ion panel or modules have a fluid loop that runs through them. So I've used that, and there's a sump there that has a heater in it. So when it's cold out, that little controller down here, which currently says it's 14.2 degrees Celsius in the sump, that will kick on a heater to heat the batteries. And when it's warm out, it'll kick on these fans that blow through this radiator to exhaust heat out of the batteries. So that keeps those nice and safe. There is also a protection down here. That's under voltage, over voltage protection. So it disconnects everything. Mostly it's used for under voltage in case for some reason the batteries get too low. It'll disconnect everything except for the solar so that the solar can recharge the batteries. All right, now to the main equipment. This is my telescope. It's a plane wave 12.5-inch corrected Dahl-Kirkman design, or CDK. Has a focal length of 2,541 millimeters, which may not mean anything to you. No worries. Just know that it means it zooms in on a very, very narrow spot in the sky. There's a bunch of stuff riding on it, a power switcher, remote controllable USB hub. This is the focuser rotator, so it moves the camera in and out to achieve focus, and it can rotate the camera to achieve the field of view that I want. This is a filter wheel, so this camera is actually monochrome. It doesn't have Bayer matrix over it, so it doesn't shoot color pictures. The reason for that is because color cameras are a lot less sensitive. So when you're shooting deep space stuff, it's usually best to use a mono camera for that extra sensitivity. And then this has a red, green, blue, clear filter in it, as well as what's called narrowband. So it has hydrogen alpha, oxygen, so O3, and sulfur, or S2, narrowband filters in it. And so this allows me to take different pictures in the different color ranges and then put those together to make a color picture. Down here is the new computer I just put in order to run all the telescope and gear. It's a lot more powerful, and you don't need the power for running the gear or capturing the pictures, but what you need the power for is processing the pictures after. So this camera is a 61 megapixel camera. So that takes up a lot of space, and there could be 100 or more individual frames at 61 megapixels that need to be processed and calibrated and stacked and everything in order to get a usable picture out to me that I then further tune and tweak locally. But so that computer will be doing that. Let's see. This runs the fans that's in this telescope to equalize the temperature. This runs the dew heater for the main mirror and the secondary mirror that's at the top. I'll step around here and show you that. So there is the secondary mirror suspended on those two crisscrossing bars, and it has a temperature sensor and a heater there. This is a guide scope and a guide camera. So this takes pictures at the same time that this does, but this is monitoring much more frequently, and it's looking for the stars that it's looking at to start shifting brightness in one direction or another to adjacent pixels, and it'll send corrections to this mount while it's moving across the sky tracking an object. These are all counterweights, so you want everything up here to be balanced with what's down here so that the gearing and motors and everything in here don't have to work as hard to actually keep something moving. So that's what that's for. This is also all balanced, so everything from here back balances with everything from here forward, so that the tracking in this direction also is balanced and doesn't take a lot of energy. This is a flat panel. It's used for taking calibration frames where the like a dust donut in your picture, or chromatic aberration, or aspherical distortions, or anything like that. The pictures pointing straight at this with the camera, that can be added or subtracted from your actual pictures of your astronomy stuff in order to calibrate them so that those dust donuts and aberrations and everything get taken out. So it helps produce a very nice, flat, pristine image. Okay, so this one is my observatory buddy's Mark. His telescope, it's an Celestron Edge HD 11-inch. He's got a very similar mount to mine, so all that operates the same, the counterweights and all that stuff. He has a very similar focuser rotator, a little bit narrower because of the limited back focus distance that this telescope provides, but basically identical in theoretical operation. Filter wheel, monochrome camera, just a different camera. This, I have one on mine as well. This is actually the thing that the computer interfaces to, and then this controls the motors and everything. His NUC that runs his imaging gear, network switch, his flat panel. We also have security cameras that are aligned with the telescopes so that we can see the scopes themselves. If we need to and judge, like if the rotator is going haywire and it's getting ready to loop this cable around or something, we can stop it, observe it with the camera, rotate it safely back to where it needs to be. That's less of an issue nowadays, but you know, historically in other software I've had issues. I can explain that later, but there's the camera for mine. I already pointed out that camera, and there's another camera over there, so those two just give big overviews inside. All this junk has nothing to do with astronomy. I travel the country full-time in a motor coach, so this is storage. This is a swamp cooler and some other miscellaneous wiring and supplies. This is what rolls the roof. 24-volt, 1 horsepower DC motor, 60-to-1 reduction gearbox, a number 40 chain, and it's connected to the roof, and then all the way out at the other end, there's, actually I can lift this up here and you can see that. There is a long bar that the chain runs inside of and then on top of. So the part on top connects to the roof and pulls it or pushes it out, and then the return for the chain goes inside the tube, so it helps reduce any sag due to gravity or something like that, which is a common problem on remote observatories like this. Control. So this is a reversible variable speed DC motor controller. This is a custom board I fabricated in order to control this. And it talks to a computer back here. So this is the other control board and control system for the flap. And then all that talks to this computer over CAN bus. And this puts that data out onto the network to this computer, which monitors everything else that's going on in the observatory. Monitors weather, monitors whether I'm imaging with my stuff, Mark is imaging with his stuff, and so it will multiplex the roof controls. So for example, if I'm imaging and Mark's imaging both at the same time, and then my imaging run completes and my system says, okay, close the roof, it will check and make sure Mark is done before it closes the roof. And if it's not done, then it'll wait until his system tells it to close the roof. That's relatively new code I just added, but pretty proud of that. I guess we can step outside real quick. So this is the outside of the building. When we moved it here to Astronomer's Paradise, I went ahead and put metal siding on it because the number one maintenance task that had to be performed here was painting the building. Even though it came with a urethane that was rated for like 15 years or something, I literally had to repaint 2/3 or more of the building every 6 months. That's just how punishing the environment is out here in the desert Southwest. It's basically like a constant sandstorm whenever the winds kick up, or sandblasting. So here's the roof roll off. You can see the insulation I've done inside the roof, more storage up there in the loft, and the rest of this structure just supports the roof while it's rolled off. You can see the rollers there. On this side, you may be able to see, there's a V-track, and then the rollers are V-notched. So the rollers on this side index into that track when it opens and closes. This side free floats. So that helps prevent binding in case the roof is slightly shifted or something happens while it's racking in and out. So it will automatically, this side being floating, you can sometimes hear one of the rollers pop as it readjusts. So it helps keep things moving freely. I do also have cameras on the outside, one on each corner, and they're pointed so that it gets full 360-degree coverage. Hope that didn't jar too much in there. Anyway, these are the solar panels, 4 300-watt solar panels, so 1,200 watts total. This is my AllSky camera. So that takes a picture of the whole sky, horizon to horizon, all the way around, and uploads that to my AllSky Camera website. And then I process all those pictures at the end of every night to do a time lapse of the night. This is a astronomy specific weather station. So it senses moisture, and it has an IR cloud sensor and a sky luminance sensor. Then I have 2 more weather stations that travel on the roof. The one on this end of the roof up there, that is a weather flow tempest. And so that one is nice, no moving parts, nothing to really break down. It uses ultrasonic for wind speed sensing and direction, and it uses haptics. So if rain is falling, it senses the impact of the rain on the top of it to sense how much rain is falling. The weather station on the other end, that's an old school ambient weather station. Historic, typical moving parts stuff, weather vane, anemometer, and then a rain cup with a little flappy cup inside that dumps out and shows, how much rain is coming down. It also has, both of them have solar radiation sensors and UV sensors and all kinds of other stuff built into them. So that's what the inside computer is monitoring all the time, all 3 of these weather stations, to make sure that it's safe, both from a no cloud perspective and from a weather, wind speed, rain, condensing moisture, all that kind of stuff. Monitors all that. So this is a linear actuator. This is what opens and closes the flap. And yeah, that's where it's patched through. This small antenna is a wireless radio that is on my buddy's Wi-Fi here in the observatory area as a backup. I don't use it as the primary connection. This is a cellular antenna that is the primary connection to the internet. So there are no outside wires that come into this. Everything is cellular, wireless, or solar. and that takes care of everything. So it's very resilient, very off-grid. So I don't, and the other thing too, since the internal computer is constantly monitoring all the conditions, it doesn't need internet access to operate safely. So if I or Mark hop into our systems and we get an observing session going, then and then we lose internet for some reason, it's no problem. It'll keep running until our sessions are complete and it closes the roof, or the weather conditions dictate that it needs to close the roof. So yeah, I'm just wrapping up my trip here to do some maintenance, swapped out some computers, did some, put a guide scope on, changed that out, just various random things, but getting ready to head back to Las Vegas where my coach and my wife and our fur babies are, and ride out 2022 there at the resort. So hope this came out okay. Hope I didn't say too much, and yeah, maybe informative. Oh, one other little quick thing I forgot to mention. If you notice, there's some straps here, some strap steel, 1/4-inch plate steel with holes drilled in it. On the flap, there are vertical rods, or they're vertical right now because it's open. Same thing here. There's a 1/2-inch bolt, and then you can see sticking up above the walls there, the same type of plate steel. So when the roof closes, the 1/2-inch bolts interlock into these holes and keep it safe from blowing off if there's high winds. And I've actually recorded wind speeds here. I know for sure 78 miles an hour, and maybe even a little higher, maybe up into the 80s, but I can't remember for sure. So it definitely gets windy, and these definitely keep the roof safe. The building itself is anchored, so these verticals are anchored to the ground here and anchored into the 2x4 wall joists in the building, so that anchors it. And then you can see these straps, every so often those are anchored into the concrete and screwed into the floor joists, the 2x6 floor joists. So that helps hold the building down in high winds. You know, if it gets too windy, it's definitely still going to have a problem, but at least this helps keep things safe. So anyway, yeah, thanks for stopping by, and hope this was informative and enjoyable. Catch you next time.